Hello and welcome to part 4 of our chapter 7 videos. For this part we're going to be finding a normal values example. So before we went into we're finding a value for x, right? So we're finding a value for x now, and we're going to go through the steps in the example problem going forward. So suppose we want to know what gestational length is less than 97.5% of all gestational lengths. So step 1, we're going to state the problem. So we're going to let x represent gestational lengths. The prior problem established x normally distributed as a mu of 39 weeks and a standard deviation of 2 weeks. We want the gestational length that is shorter than 97.975 of all gestations. Remember, this is the key words here, less than 97.5% of all gestational lengths. That means that we're looking for the bottom 2.5% of all gestational lengths, meaning it's the very end tail of what we're looking for, because 97.5% of all gestational lengths will be greater than this value here. So this is equivalent to the gestational length that's longer than 0.025 of all generations. So remember, if you want to move the decimal over, we can turn that into our percentages here, right? And if we add 97.5 plus 2.5%, we're going to get a value of 100%, or 1, right? And we all know that the sum of all total probabilities has to equal 1. This is what we learned back in chapter 5. So here's our example continues. So step 2, we're now going to use table B to look up the z value, right? So remember, we're using our z percentile here. So we're using our z percentile of 0.025, right? Because we want to find the gestational lengths that are greater than 97.5%. So we're looking for the bottom 2.5% here. Remember, so less than 97.5%, so it's going to be in the right tail, greater than 2.5% in the left tail. Remember, table B is all using left tail. It's the cumulative probability from that value and to the left. So here we have a z lookup in the table shows. So here's our z, 0.025. Remember, this is like a z percentile. So we're trying to find the percentile of 0.025 and what the z-score associates that with. So when we go, we're going to be looking for 0.025. We find it here, and then we look and see what z-score that's associated with. So once again, this is a little table's chopped off, really easy to see, but if you go into the book and table B in the back, you can see it with all the other numbers there. So when we go here, we have a z of negative 1.9.06. Remember, this is the hundredths, and this is our tenths of z-score. So this is going to equal negative 1.96. When we have a negative 1.96, you might be saying, that's interesting, right? Because when we did 0.975, it was equal to, right, a z percentile 1.975 is equal to 1.96. And you have to think that this graph here, this table B, this normal distribution here is symmetrical and it's evenly distributed, right? So what is at the very middle is 50-50 on each side, right? At the very middle at 0, at 50% p-value is a 0 z-score, and everything to the left and right is always congruent with each other. So a z-value of 1.96 is going to be the inverse, a negative that will cover 1 minus this, or the complement of it. So just kind of keep that in mind. If sometimes it's hard to see that, but remember that when we're looking at this table in the back, that it's equally distributed and it's symmetrical. So, and that's part of our whole 68, 95, 97, 99.7% probability, right? That if we go 1 standard deviation out, it's going to encompass 68%, 2 standard deviations cover 95%. It's equally on both sides of the distribution. And same thing goes when we start talking about z-scores, that they work in tandem with each other. And this goes back to our rules of probabilities, right? Those 4 basic rules that we cover in the course, that the total probability is going to sum to 1. The probability of 1 minus the probability will equal the complement of that probability. All probabilities have to be between 0 and 1. All of those, the first 4 kind of start getting into this, because what we're doing is we have these probabilities and we're using, the symmetry of the graph to solve for it. So, no, a little fancy way to show that. And then here's the graphical representation of it, right? So when we look at negative 1.96 z-score, and that's that value to the left, that encompasses 0.025%, right? And that's what we're looking for. So anything that this value is in greater will be encompassed at 97.5%. So there we go, we sketched it, which is shown here. Once again, I am not a great artist by any stretch of the imagination, but if you think sketching will help you, 100% always sketch the problem out. I will do my best to show sketching, but as you can see here, this would be my normal distribution. It's not very good at all, so I'm not a very good drawer. But you can still get the points, where if you're looking for certain values, you can cut them off, and that might help you visually see what you're trying to do here. So you would sketch this, and then you would understandize it. So remember, we're solving for an x value here, where we have our mu plus our z percentile multiplied by our standard deviation. Remember that we had this as a normal distribution, right? We're going to let x be distributed as normal distribution of 39,2, where our mu was 39, our standard deviation was 2, and we plug into our value here to solve for x, and when we find our z percentile, negative 1.96, multiply it by our 2, add it to 39, we're going to get 39.05, or 35.08, excuse me there, I was looking all the way over here, which is approximately 35 weeks. So we'd say, that anything after, if you had a birth less than 35 weeks, 97.5% of births are going to be greater in weeks comparatively gestational wise. So the 2.5 percentile gestation is 35 weeks. So that covers finding z percentiles, finding a z-score. The best thing to do with the z-score and the z percentiles is practice, 100% practice. I think the biggest part when we're doing z-scores and z percentiles is understanding when you have like a z and then an underscore number, that this is the same thing as our z percentile. So we're looking for the percentile to find the z-score. And then when you're solving to find a z-score, remember to always equals a z value at the very end. And if you know you found a z value, then you have to go to table B. My personal thing is when students get overwhelmed with this topic is that most students can do and find a z value. It's then taking that next couple steps, going to table B, find the z percentile, or finding the z-score, find the z percentile, or working its way backwards. It has a couple more steps after that. So most people can get to the z-score, but then they forget where to go after that. So if you always know in your problem what you're solving for, and then at the very end put equals z, and then if it's a z-score, I got to go back to table B and I got to go and do something there. You're going to keep going on those next steps in order to solve the problem appropriately. And the best way to get that ingrained is to keep practicing it. All right, so now we're going to do 7.4, which is assessing departures from normality. So every time we're talking about here, we're talking about a normally distributed, data set, right? And a normal distributed data set is going to be one that's more symmetrical. Once again, I'm not a great drawer. So the best way to show this, though, is graphically, and we used histograms and QQ plots to show either a normal distribution or how there is skews, which will show that it is not a normally distribution. So here we have a histogram and a QQ plot. So you can see that here it's a normally distributed data where we have the correlations mostly along the line, very well correlated, we might say, and then we have a distribution function here that is relatively normal. Whereas now here we have a negative skew. Remember, if you look at a negative skew, if you think with a negative skew like that, remember way back in chapter 3, I believe it was, remember when you're looking at negative and positive skews, if you look at your feet, right? So your left foot how you have your little toes all the way to your big toe, and that would show a negative skew, and then it's the opposite for your right foot would show a positive skew. And then when we look at it on a more dot or QQ plot here, you'll notice that it doesn't all tend to be on the same line, so it shows you this negative skew function here. So the negative skew will show up an upward curve on the QQ plot. And then here we have a positive skew, so remember this would be your right foot. And then as you can see here for the QQ plot, has a downward curve there. And then if you have like a leptokurtic, way back in chapter 3, remember all these things, they all come in together. So remember the first part of the semester, we got this foundation, and now we're using this foundation to build upon it, and this is kind of showing how it all comes together. So remember, leptokurtic is high peak with skinny tails. So look like this. Remember, high peak, skinny tails, leptokurtic. Remember, there was a picture of that of the two kangaroos looking at each other with their long, skinny tails, and that'd be leptokurtic because kangaroos like to leap. And then you can show an S shape on the QQ plot, like that. We'll show you more of leptokurtic. So this is just going back for departures from normality, right? Majority of this course, we're not going to talk about departures from normality. We're going to just stay focused in normal distributions. More advanced statistics start going into different types of non-normal distributions, and then you'll learn the difference between parametric and non-parametric study designs. But for the purposes of our class, we're going to be dealing primarily just with normal distributions, but to show you what it would look like graph-wise with not normal and how to associate that. And there's different statistical tests you use moving forward. But like I said, for the purpose of this class, all our problems are going to be normally distributed. And that ends chapter 7. Chapter 7 is a little long, and it has a lot of information on it, and there's multiple steps to it. So once again, the more practice you can do, the better off you are. Out of all the chapters in the book, this is the one where if you go online and just type in normal distribution and want to do even more practice problems or do even more things on your internet, there is a plethora of access for you on there to do. Every stats course will 100% always go through normal distribution, and so if there's any question on normal distributions, just head online and you can definitely find more. Always feel free to email me or contact me, and I will be more than happy to discuss any questions you have or any concerns over the course. All right, have a great day, and I'll see you all in the next video.